Good morning, students. Today we are going to discuss about stability of coordination compounds. Stability of coordination complexes can be interpreted in two different ways. The first one is thermodynamic stability and the second one is kinetic stability. Thermodynamic stability of a coordination complex refers to the free energy change of a complex formation reaction. Kinetic stability of a coordination complex refers to the ligand substitution. In some cases, complex can undergo rapid ligand substitution. Such complex are called labile complex. In labile complex, the bond formed between the metal and the ligand will easily be cleaved. However, some complexes undergo ligand substitution very slowly or sometimes no substitution will occur. Such complexes are called inert complexes. In inert complexes, the bond formed between metal and the ligand will be much stronger. Now let's understand what is stability constant. The coordination complex is said to be more stable if the bond formed between the central metal atom or ion and its ligands are found to be much stronger. The stability of a complex refers to the degree of association between two species involved in an equilibrium. Let's understand this statement with the help of an example. When cuprous ion is treated with ammonia molecules in the ratio of 1:4, we get tetraamine copper 2 plus ion complex form. Stability constant for this reaction will be equal to concentration of the complex formed divided by concentration of reacting species. So if more the concentration of product is formed, the value of stability constant increases. So we say greater the value of stability constant, greater will be the stability of the complex. Now let's try to understand about stepwise stability constant and overall stability constant. For that, let us consider the complex formation Ml3 in aqueous medium. This complex can be formed in a single step or it can be formed in 3 steps. If these 3 ligands are added to the metal ion one by one, then the formation of the complex Ml3 can be supposed to take place through 3 different steps as shown below. When the central metal atom M is treated with the ligand L and forms a complex of the type Ml, stability constant K1 for this reaction can be written as concentration of the product form, that is Ml, divided by concentration of the metal M by into concentration of the ligand L. When this complex formed Ml is treated with another ligand L and forms a complex Ml2, in the same way you can write the stability constant K2. This K2 value will also be equal to concentration of product form divided by product of concentration of reacting species. This K1 and K2 we will call it as stepwise stability constant because the complex is getting formed in the stepwise. And if you consider the third step, the complex Ml3 is formed. So the K3 value will be equal to concentration of Ml3 divided by concentration of the reactants Ml2 into concentration of ligand. And if you consider the overall stability constant, it will be the product of stepwise stability constant. If we represent the overall stability constant as beta n, then this beta n value for this complex formation will be equal to stepwise stability constant products, that is K1 into K2 into K3. Generally, stepwise stability constants are represented by the symbol small k, and the overall stability constant is represented by the symbol beta. Now let's talk about instability constant or dissociation constant. Generally, coordination complexes are stable in their solutions. However, the complex ion can undergo dissociation to a small extent. To which extent it is going to get dissociated depends on the strength of the metal ligand bond. Stronger the bond formed between the metal and the ligand, lesser will be the dissociation. In aqueous solutions, when complex ion dissociates, there will be equilibrium between undissociated complex ion and dissociated complex ion. Hence, the stability of the complex can be expressed in terms of dissociation constant or instability constant alpha. Let us consider the dissociation of tetraamine copper 2 plus ion in aqueous solution. This complex will dissociate to form Cu2 plus ions and 4 amino molecules. The dissociation constant or instability constant alpha will be equal to concentration of the Cu2 plus ions into concentration of ammonia molecules raised to the power of 4 divided by concentration of the complex CuNH3 4 times 2 plus. We can say the dissociation constant alpha will be the reciprocal of the stability constant. There are two factors which affects the stability of the complex. The first factor is the nature of the central ion. Greater the charge density on the central ion, greater will be the stability. This is because if charge density on the central ion is greater, then it will have more thirst for the electrons. So it forms a stronger metal ligand bond. So the stability of the complex increases. The second factor which affects the stability of the complex is the chelating effect. If the chelating ligands are present, then the entropy of the complex increases, which in turn increases the stability of the complex. In the examination point of view, if they ask you among the complex K4FeCN6 and K3FeCN6, which one is more stable? Here, the ligands are the same in both the complex as well as the central metal ion is same in both the complex. But what's the difference is that the oxidation state of the central metal ion. In the complex K4FeCN6, the central metal iron is in +2 oxidation state. Whereas in the complex K3FeCN6, the central metal atom ion is in +3 oxidation state. So we know greater the oxidation state of the central metal ion, greater will be the stability of the complex. So the complex K3FeCN6 will be more stable. Students, kindly practice these questions in your notebook.